All right, continue further. All right, now let's look at acids and bases. So an acid is a molecule or ion capable of either donating a proton, such as hydrogen, or in other words, hydrogen ion, which is H+, without an electron, so just a proton, and or some neutrons, known as a Bronsted-Lowry acid, or capable of forming a covalent bond with an electron pair, known as a Lewis acid. Yeah, so again, notice that, so it's donating, so an acid is either donating a proton or forming a covalent bond with an electron pair. Interesting. Yeah, in both cases, it wants to be more negative. Notice, because it's getting the electron pairs, it's getting more negative, or it's removing a proton, removing a positive charge, is becoming more negative. So the first category of acids are the proton donors, or Bronsted-Lowry acids. In the special case of aqueous solutions, proton donors form the hydronium ion H3O plus and are known as Arrhenius acids. And an aqueous solution is a solution in which the solvent, or which is a substance that dissolves the solute, or the solute is water. And the word acid is derived from the Latin acidus or acere, meaning sour. So yes, so just that special case here. So if in aqueous solutions are in where the solvent is water, you get proton donors form the hydronium ion H3O+. So you can determine it's an acid by if this is being formed. Going further, so there are three definitions in common use of the word base, known as Arrhenius bases, and basically. Actually, there's three of them. So there's known as Arrhenius bases, which give OH- in water. Bronsted and also -Lowry bases accept protons, and Lewis bases donate electron pairs. So notice this is the reverse of that acid. So this is donating proton. The other one is it's accepting proton, and then the other one is accepting forming electron pair. This one is donating electron pair. Yeah, so these bases want to become more positive. So all definitions agree that bases are substances which react with acids as originally proposed by G.F. Ruel in the mid-18th century. Let's continue further. So here's an illustration of the types of definitions of acids. So acid-base reaction theories as superset and subset models. So you have Lewis acid and base model. So acid accepts electron pair. Base donates electron pair. This is circa or from 1938. And notice there, this encompasses all of them. And then you have the Arrhenius model. This acid gives H plus, and bases give OH minus in H2O, so aqueous solutions. And note this H plus, just the Arrhenius model is for aqueous solutions, and the symbol H plus is interpreted as a shorthand for H3O plus. It's just shorthand, so it's actually giving H3O plus, because it is now known that a bare proton does not exist as a free species in aqueous solutions. So you can't just give a proton in aqueous solutions, and it's not going to exist as that. It's going to exist as this. More commonly as this H3O+. Then you have the Bronsted-Lowry model. So this Arrhenius model is inside this one, which is inside the overall one, about donating and accepting electron pairs. So Bronsted-Lowry model acid gives protons H+, and base takes protons. This gives protons, another one takes it in liquid, gas, and solid. Is from 1923, and this one's all the way from 1884. The Arrhenius model, and that one is. Yeah, it's specifically giving or forming H3O+, so hydronium ion, and then the bases give OH. Alright, continue further. So bases and acids are seen as chemical opposites because the effect of an acid is to increase the hydronium H3O plus concentration in water, whereas bases reduce this concentration. So yes, they're considered opposites of acids. Bases, it's always, basically wants to increase this, another one wants to decrease that. So MES memory tool, acids become more negative and bases become more positive, as I've been stating. In the Arrhenius theory, so I keep pausing and looking up the pronunciation on Google after years of people telling me I can't pronounce. But anyways, In the Arrhenius theory, acids are defined as substances that dissociate in aqueous solution to give H plus or hydrogen ions. Yeah, so it gives this hydrogen ions, but it forms the H3O plus. While bases are defined as substances that dissociate in aqueous solution to give OH minus hydroxide ions. This was the first modern definition of acids and bases. It was devised by Svante Arrhenius in 1984, which led him to receiving the Nobel Prize in Chemistry in 1903. And I'll just put this here. Yeah, I'll just put this note here in brackets, so this inline commentary. So this is forming H3O plus. And then close this and then put this on top. And this is bottom. All right, going further. So the Bronsted-Lowry theory, also called, this is going over it again. This was all summarized in here, but I'm just going to read it out further. So the Bronsted-Lowry theory, also called proton theory of acids and bases, is an acid-base reaction theory which was proposed independently by Johannes, Nicolaus, Bronsted, and Thomas Martin Lowry in 1923. The fundamental concept of this theory is that when an acid and a base react with each other, the acid forms its conjugate base, and the base forms its conjugate acid by exchange of a proton, the hydrogen cation, or H+. This theory is a generalization of Arrhenius theory. So Arrhenius theory is part of that, and this is more general of it, as opposed to just aqueous solutions. Going further right here. So here it is. This was actually what is written here. So the Lewis theory is a generalization of the Bronsted-Lowry theory. And in 1923, Gilbert N. Lewis wrote, "An acid substance is one which can employ an electron lone pair from another molecule in completing the stable group of one of its own atoms." So in other words, it's accepting an electron pair from another molecule. Okay, and then in the Bronsted-Lowry theory, acids and bases are defined by the way they react with each other, which allows for greater generality. This definition is expressed in terms of an equilibrium expression. Actually, I just go backwards again here. This was here. This theory, the Bronsted-Lowry, is a generalization of the Arrhenius theory, and then the Lewis theory is a generalization of the Bronsted-Lowry theory. So yeah, these aren't the same things. Initially, I was thinking that I just read the same thing. No, this is the more general. So Lewis is more general of Bronsted, and Bronsted is more general of the Arrhenius theory. And hence this, you go Lewis, Bronsted, Arrhenius. So yes, going back further here. So yeah, so basically the definition for the Bronsted-Lowry theory is defined based on how by the way they react with each other, the acid and bases. Definition is expressed in terms of an equilibrium expression, acid plus base. And you have this line right here, which indicates a reaction going either way. And then you have conjugate base plus conjugate acid. And the word conjugate means related or joined together. So with an acid, HA, the equation can be written as this hydrogen and an acid, can be written symbolically as HA plus B, a base. The reaction goes such that you'll have an A minus. Yeah, so initially, this is the acid. This acid A is giving giving a hydrogen proton. It's giving a proton away, and then it becomes negative because initially it's not negative, and then this becomes A minus, or becomes more negative than it used to be. So this becomes A minus, which is its conjugate base. So now it's acting like a base because now it wants to pick up a proton or a hydrogen, and then this base, once it picks up the hydrogen, so this hydrogen goes here. It goes there, so now you have an HB. Now you have this HB plus, so it becomes more positive. And now it's more positive than it naturally is, so it wants to lose that, so it wants to become like an acid. So in other words, this acid and this base become a base and an acid. So the conjugate base is an acid with a hydrogen ion proton added to it. And the conjugate acid is a base with a hydrogen removed, a hydrogen ion. Removed from it. So yes, very interesting. And here's another example right here. So reaction of NH4 to NH3. And yeah, I think this is supposed to be a subscript. So this is subscript, so it's 4H. And it becomes 3. So you have this NH4 right here. And then this is OH like that, so plus that. So this is the base, OH. is an acid. So then this one's going to pick up one of these hydrogens. So this one's going to go over to here, and you have a OH. This can be an OH2 or H2O. And then this acts like a conjugate acid right here. And then you have the conjugate base now. Because it used to be an acid, now it's a base because you removed a hydrogen. Now it wants to pick up back its hydrogen. All right, going further. So in a chemical reaction, chemical equilibrium is the state in which both the reactants and products are present in concentrations which have no further tendency to change with time. So for example, if this is equilibrium, it's going to go back and forth such that concentration of this and this aren't changing. They're just intermixing back and forth with each other. So with tendency to change with time, so that there is no observable change in the properties of the system. This state results when the forward reaction proceeds at the same rate as the reverse reaction. The reaction rates of the forward and backward reactions are generally not zero, but they are equal. Thus, there are no net changes in a concentration of the reactants and products. Such a state is known as dynamic equilibrium. So in chemistry, pH, lowercase p, then uppercase h, denoting potential of hydrogen or power of hydrogen, is a scale used to specify the acidity or basicity. Let's try that again. Basicity of an aqueous solution. Now, acidic solutions with higher concentrations of H plus ions are measured to have lower pH values than basic or alkaline groups 1 and 2 in the periodic table solutions. So basically less than these alkaline solutions. Acidic equals high H and equals low pH. So the pH scale is base 10 logarithmic, which is a non-linear scale, and inversely indicates concentration of hydrogen ions in the solution. So the bigger the number, the lower the hydrogen ions. Smaller the number, the more of it. So formulas that you'll have pH equals to negative log of this H3O plus this hydronium ion in there. And then if you do some mathematics here, take the 10 to the power of everything. This just means the same thing. So you'll have 10 to the power of negative pH is equal to the concentration. This is how it's written. This means concentration, these brackets right there. Which equals to, the concentration of this hydronium ions, equal to this. And then the logarithmic is defined such that you can solve this pH by equals to this negative log. So you bring this negative out. And basically the negative log of this concentration is equal to the pH. So you can see my earlier videos on logarithmic functions to learn more about this. But anyways, so the higher the pH, the more exponentially H3O plus decreases. Because the H3O plus in aqueous solutions, that just means this is just higher hydrogen. So the H right there. And so the higher it is, the lower this is. So it's inversely proportional. So at 25 degrees Celsius, solutions with a pH less than 7 are acidic, or which have high H plus, and solutions with a pH greater than 7 are basic, which have low H plus. So for example, here is some examples right here. So neutral's in the middle right here. Acidic is at the bottom with the number 0. And then so notice it's a exponential scale. So each one is a 10 times increase. So if this is the absolute bottom right here, hydrochloric acid, it has a whole lot of H. The 0 is the absolute one that has just all hydrogen. And then you can go up higher. This lemon juice is very acidic, and notice each one is 10x bigger. This is 10x bigger, so it's 1, 2, 3, 4. You're getting exponentially bigger and bigger and bigger. So then something super high here, sodium hydroxide, and the household bleach. This is very basic. So this wants to accept as much electrons as possible, and these want to give up as much. So lemon juice, vinegar, soda pop, orange juice, tomato juice, coffee, and you have milk is more neutral, and you can even tell. So pure water is just right in the middle, which is interesting definition how they got it like that. And then you have blood, which is slightly more basic. So blood is slightly more basic, but still on the neutral side. You have eggs and milk of magnesia. I think I go over that in a bit. And then you have the detergent, ammonium solution, soap. Soap is more basic. And these want to pick up a bunch of acidic stuff. And you have a bunch of stuff that if you put orange juice on your hand, it sticks to it. Now you have soap. It's basic. It reacts with it, and you can clean up your hands very well, and so on. And household bleach, basic, very basic as you would expect to clean out orange juice stains and so on. Anyways, keep going further. So that's figure 1. enough size. So figure 1, the pH values for several common materials. And a note, milk of magnesia is a common laxative, which helps in pooping. A detergent, I think I wrote detergent here. Yeah, actually, that's right here. So detergent or laundry detergent to clean your laundry. So a detergent is a surfactant or a mixture of surfactants with cleansing properties in dilute, low concentration solutions. Surfactant are compounds that lower the surface tension or interfacial tension between two liquids, between a gas and a liquid, or between a liquid and a solid, basically lowering that surface tension. Between substances. And surface tension is the tendency of liquid surfaces at rest to shrink into the minimum surface area possible. And here's just a GIF here to illustrate what I mean by that. So before he puts the surfactant inside, let's try to get it to stop before. Yeah, so before he puts it, you have them all of them are together. And then once he puts the surfactant, it lowers the surface tension. So the higher the surface tension is on the outer side. And basically, those want to pull in all together there. And these particles just all spread out over there. And here's a better image right here, or a different kind. So this one here, before, let's just press the stop button. Yeah, stop right there. So before, it's just like this. So all the surface tension on across this whole liquid is all the same. So everything's pulling at each other at the same strength. And once he puts a surfactant inside here, this makes this lowers the surface tension. So then the highest surface tension is on the outside, and those are all pulling it out. So then this string gets pulled all out and into a perfect circle. So let's see right here. Drops it, and now you have a perfect circle, which is this is quite amazing stuff there. Anyways, let's continue further. And yeah, so here's a periodic table of elements, and it shows you the types of elements. So alkali metals are these this one right here, this first row, and then this one here, that's an other non-metal. So I guess those would be here. And let's see where else. The alkaline earth metals are over here in this row. This column 2. Then you have some rare earth metals here, these ones here, and these across there, and so on. Let's see what other types there are. Halogens over here. Yes, interesting. And so this is a periodic table of elements, and then note the alkali metals group 1 and alkali earth metals group 2. Those are the basic ones. So that's basically why I added that there, just to illustrate this part here. So it has so basically acidic solutions has high H plus ions that are measured to have lower pH values than basics or alkaline solutions. So these are groups 1 and 2 in the periodic table. The periodic table of elements right here. So these ones are basic. Anyways, continue further. All right, let's look at acid strength. So acid strength is a tendency of an acid symbolized by the chemical formula HA. So acid has a hydrogen to give, and that's why you have it there. To disassociate into a proton, H plus, and an anion, A minus, or a negative ion. So the dissociation of a strong acid in solution is effectively complete except in its most concentrated solution. So notice the arrow is straight as opposed to that double arrow going back and forth in equilibrium. So this one it's a strong one. It basically completely dissociates into giving up a proton, and then it keeps its anion. So you have HA plus S goes to SH plus plus A minus, where S is just a solution and so on. Or right here, actually, that's solvent molecule in the solution. So where S, put this here, where S represents a solvent molecule, most commonly is water. So a weak acid is only partially dissociated with both the disassociated acid and its dissociation products being present in solution in equilibrium with each other. So HA plus S, and then you have the double arrow right there. SH plus, so the A gives up the H to the S, and then you have it an anion. Yeah, so this A minus. So HA plus S is in equilibrium with SH plus A minus. And acid strength is solvent dependent. So it depends on if it's water or something else and how strong it is, and so on.